So, hey guys, I'm Katherine Whitlock, and my talk is going to be on compilers, interpreters, and what they are. Okay, so you're writing a program, right? And it's in some language that you are required to write in because maybe customer has requirements you need to write in Java or Python or something, and you're like, can't I just do this better in some sort of other syntax that I really want to do? And so that's kind of where the basis of compilers came from, which is we had a basic language the computers operate on, assembly, and you might know that. And then we have languages that build on top of other language, which is built on top of other languages, which build on top of other languages. And this idea of translation from one language to another is what compilers and interpreters are. And so that's what my talk is going to be about. All right. So a lot of you guys may be like, okay, what's a compiler? Like, how does this work? What goes on? How are the processes that happen inside of it? And so a lot of people, you're like, okay, I'll give it two numbers. I'll tell C int main equals something, and we'll return 2 plus 3. And I give it to the compiler, and the compiler's just like, okay, your program's done. And you run it, and it gives you 5. And it's sort of like confusing because you don't know really what's going on inside of it, and you want to know more. So let's try to understand how compilers and interpreters work. So to go over that, we're going to look at what they do. So looking at the box of a compiler or interpreter. How do they work? Opening the box. And why are they important? What do they mean for us as programmers? So what is a compiler? Well, at a basic level, at a higher level, we have a compiler. And the point of a compiler is to try and interpret the meaning of what you tell it. So in our previous program, 3 plus 2, we're telling the compiler that we want to add two numbers, 3 and 2, and we want to get the result out of that. But to a computer or to a program, that's just bytes. That's just characters, strings, whatever you want to think of it as. And so what the job of a compiler is to try and figure out the meaning that lies behind the representation. In this step, once we've understood what your program wants to do, whether you want to print out hello world, or you want to add two numbers, or you want to, I don't know, calculate the nth number of Fibonacci sequence, the compiler takes that and represents it in a way that the computer can understand it. It's a program. I think this is important. To me, when I was learning how to program and stuff like that, I learned on BASIC, so kind of gross, but whatever. So I would write a basic program, the compiler would take my basic program, and then it would put it off to a microcontroller, and the microcontroller would run it. And I didn't know anything about where my program was going between my program and the microcontroller. I just know that some fancy stuff happened, and somehow it ran, and it gave me the right answer. But in reality, a compiler is a program just like any other program you write, any other software system. It takes input, it gives you output. Garbage in, garbage out is standard concept. So, I mean, it's just another program. Compilers and interpreters are programs. They all have an entry point. They all have a main function that takes something and you run it. All they do, and this is really important, is they just process text. So when you're writing code, you aren't writing it as I hope you're not writing it in like a spreadsheet or a graph or something, because that's really annoying. I know, actually I take that back. There are a couple languages out there that make you like draw out things. We're not talking about that. But so at a basic level, compilers just process text. You give it a text file. It draws meaning from that file. It figures out what you're trying to do. It is written by mortals, like you, me, everybody, compilers aren't written by people who are crazy or anything. It's written by people who are just like us, who write software, and so they decided to write a language because they felt that something was lacking in another language, or they decided to build a compiler for a language. There are hundreds of C compilers out there. You only hear about big ones, GCC, Clang, those. Maybe you've heard of the Intel C compiler, ICC, because that's another industry big one. But there are literally hundreds of C compilers out there. And a lot of people don't hear about them. But you may find that if you're at a company and they want to develop some sort of application and they've decided that a C compiler isn't good enough, you may have to write a C compiler. And it happens. So what does a compiler look like? Well, If you look at Clang, it's just an executable. So it's sort of like this mystery box. You don't really know what's inside of it. It's just there. And you give it some input, and it gives you some output. It's this gray box of complexity. But in reality, a compiler can look like this, where you have what's known as a single pass. So you take your input, you process it, and you just generate output. And that's pretty simple. There's actually a compiler that was really widely known called, it was a compiler. It was known as the Turbo Pascal compiler. And what Turbo Pascal was known for was the fact that it was ridiculously fast. It could take a Pascal program and compile it to a representation that was faster than people who could write assembly. This was back in the 80s, but at the time that was really cool, because the idea that you could write a program in this language and have a program transform it, and then have that resultant system that you wrote but has been translated run faster than if you wrote that in a language the machine itself could understand was really, really cool. And the Turbo Pascal compiler was actually written as a single pass. It was all self-contained. You had 3 floppies to run it off of. And you put one in, start up the compiler. It would do all of its pre-processing stuff. You would stick in another disk, go to run it through the internal representation, and you would put in another one to link all the files together. And it actually spit out a ton of files that were intermediate files for this. Nowadays, though, it's not really working that way. Single pass compilers are written, they're small, they're oftentimes used I'm pretty sure the JavaScript CoffeeScript compiler is a single pass compiler, and so you get them for small dialects and things like that. But modern compilers are usually written like this. You have a front end, which is where you do all of your main text processing, and you have an intermediate representation that is used between the front end and the back end, which is what takes a structure and then translates it into a way that the machine can understand it. It's pretty simple, right? I mean, there's not too much complexity there. You have one piece and it hands off to another piece. And you have one direction, you have this IR that moves from front end to back end, and that's all that really happens. There are compilers that are implemented this way. They're actually pretty simple. You use a tool such as Flex or Lex, and then you have a parser for Yak and Bison. I'll talk about that a little bit later, but I'll introduce it now. And that's contained in your front end, and then you have a tree structure. There's your intermediate representation and given to a back end, and then your back end takes that and can emit assembly. But then we get stuff like Clang and GCC, and they're quite a bit bigger. So they start out with a Lexer. And the purpose of a Lexer is to sort of figure out where unique identifiers are in your code and where text is and stuff like that. That gets turned into tokens, which is then passed on to the parser. And the parser builds a tree structure known as the parse tree from this token set. The parser then takes this tree and turns it into a simplified tree called the abstract syntax tree. The abstract syntax tree is then handed off to some sort of other process which does context analysis, figuring out where variables are and things like that. And then that gets turned into annotated AST, so you have type names and stuff like that that are inside of your structure. This gets passed off to an IR creation module, which creates the intermediate representation. And the intermediate representation can actually be a language of its own. GCC actually uses a Lisp for its intermediate representation because Lisp is such a good language for representing tree structures using cons pairs and things like that. If you're interested in why Lisp is good at that, I had a Lisp talk last year, and I talked about trees and data structures in Lisp. This IR creation gets turned into IR, which is its middle, and then gets passed into an optimization pass. And the optimization pass of compiler normally takes the intermediate representation, and if you all know the visitor pattern, this is usually a point where the visitor pattern is used in a compiler because the visitor class is created, and each optimization pass is usually made as a visitor, and you run that visitor over all the nodes of your tree. And it takes it and it simplifies the tree and it makes it more simple and can sometimes actually add other annotations to it depending on what you're trying to do. And so that happens maybe 1, 2, or 3 times. That -O flag that you use with GCC or MSVCC or Clang is actually what determines how many optimization passes the compiler uses. That is then passed on as IR still into the code generation system. code generation system generates some symbolic instructions that it uses. Usually, they're not actual machine instructions, but they're close to, so that it makes it easier so that when we run it through a machine, that is, what? Okay, there we go. So that it runs through the machine optimizer, we can optimize those simple instructions to be designed for a target architecture. Those symbolic instructions are then finally passed off to a code generator, and this code generator takes those symbolic instructions that have been simplified and generates assembly out of them. That gets turned into bit patterns, and then you get your executable. And your executable usually goes through a linker, which is actually a whole separate other program, LD or Gold or something like that. And I'm not so understanding of how linkers quite work. I know that they take different parts of of statically linked libraries and stuff like that, and they'll put them all into an executable and rename different registers and stuff like that. So, front end, back end, middle. In case you're curious, this is what the LLVM does, is all of this. And in fact, it actually does parts of this. It provides this part for you. I'm working on a language right now, and so I'm using the LLVM because this means that I don't have to worry about this stuff. And it makes my life a lot easier. So I'm not quite as knowledgeable on these areas. However, I probably know enough to answer questions if you guys are curious about certain components of this. So I'm mostly going to focus on the front end and how text processing works inside of a compiler and things like that. So the Lexer is for text. Lexer actually stands for lexical analyzer. And this means that we go through and we understand the lexical structure of the program, the text and how it flows. So some commonly used tools for this are Flex and Lex. You've probably heard about this if you've been in PLC. I heard that a couple years ago, PLC did not use Flex, Lex, and Yak and Bison. But this is a way of using regexes to represent tokens that are inside of your languages. So for instance, if we have a number, we can say that all numbers in our languages are some length, some arbitrary length, but they contain digits 0 through 9, right? So, but if it has a decimal point in it, we know it's a decimal. It's some sort of floating point number. So we use regular expressions to represent this, and those are finite state machines. And they get processed by Flex and Lex and then turned into a program. And the programs actually generated by Flex and Lex are really fast because they use table-generated scanning, and you don't write those by hand. Because if you have to change your lexing sequence and you want to edit a table-based Lexer, it's a lot of trouble and really messy. So normally people stick to regular expressions. There's this thing called maximal munch, which I actually just found out about a few days ago, and I'm having to deal with in my own Lexer, which is how do you get the longest string that matches a given keyword if you're matching all characters up to that keyword? Because, okay, so say you're matching a string. You get in some string, and you have a bunch of keywords like int and in. So in Python, or CPython, I should say. So in CPython, for example, you have keywords int and in. So how do you know to go to int instead of stopping at in? This is the maximal munch problem. And it's dealt with in Flex and Lex, but you have to deal with it manually when you're writing your Lexer by hand. A big component of lexing is reentrancy, which means that your Lexer is pure. If you want to run it on multiple threads and suddenly have all of this text coming in, because you want to be able to deal with a lot of threads simultaneously, you have to make sure that your Lexer doesn't have any state shared with any other components of your compiler, or else you can have like thread lock problems and race conditions. So if we were to take this is a valid C program. I did run this. It does work. It looks like this after the Lexer's done with it, which is just like, okay, int's an ID, main is an ID, we have a left paren, int is an ID, comma, char star, ID star, right paren, left brace, number plus, number, semicolon, r brace. You can actually get Clang to dump out the lexical structure of your program if you really want to. So if you're curious about how it works, you can actually go put this into Clang and pass it a -x and then -dump tokens. It'll print stuff out like this.
There's no return token?
It's seen as an ID. Oh, did I not put that in? I'm sorry. It's seen as an ID.
Okay.
Number plus, yeah. Sorry. There's supposed to be an ID token here. And that is actually, because the way Clang works, and this is, the way Clang works, so GCC uses this really interesting thing called the Lexer Hack. And it is not reentrant. When you run GCC, it has a problem where GCC cannot determine if int is a variable name or a type. So if you do type def int myInt, it doesn't know if myInt is a variable or a type. And so the way GCC gets around this is the parser keeps a table of all of the type declarations that you have and passes that back to the Lexer every time one is added, which creates this problem because suddenly your stream of information is not going from Lexer to parser to IR, it's going Lexer to parser to Lexer to parser to Lexer, and is in this cycle. And that creates a problem, and it's usually janky. So when Clang was developed, they actually knew about this problem because it's been around for a really long time. And they were like, OK, so we're going to figure out how to do this. We're going to do this right. So what they do is they just ignore it. They just ignore the problem. They're like, OK, guys, we don't need to know that this is an int, or if it's myInt or anything like that. We're just going to continue and say that, OK, maybe it's a variable. So this gets passed on to the parser as if it were a variable. And later on, there's a library called the Clang Static Analysis Library that runs over the abstract syntax tree and determines if this is actually a variable or a type name. And it's actually a really efficient way to do it because it gets rid of all of the problems that are associated with Lexer Hack and reentrancy and running on different threads. So a couple of you may have known of the Boknus-Nauer form in PLC. It's a way of representing grammars. A grammar is a definition of a language in terms of its terminal symbols, or tokens, and its non-terminal symbols. This is an example of a Boknus-Nauer form for a language that can add, subtract, multiply, and divide any set of numbers, any number of numbers. There is no associativity, so things that are put into this grammar are in fact evaluated as they are evaluated. You can actually add associativity by having a second non-terminal node, but I didn't want to get too complicated. I just wanted to show this how this works. So it says that some non-terminal node expression is composed of either an expression plus an expression minus expression, an expression times an expression divided by expression, or it's just a number. So if we gave it, like our previous example, 2 plus 3, it would be like, OK, word expression. 2 is a number. Cool. 2 plus expression, number. So suddenly we know that this is the rule that we match, and it's 2 plus 3. In Bison, you actually have a curly braces over here, which defines how you build your abstract syntax tree. But this is just an example of BNF, so I wanted to show how that worked. Parsing is for trees. When you parse, you build a tree. So with our 5 plus 3, this is an example I just talked about. You have an expression. An expression is yielded to expression plus expression. Then we figure out that both expressions are numbers, and those numbers are 5 and 3. But that's really verbose, and no other part of our compiler or interpreter actually needs this information. So we're just like, oh, we only need 5 plus 3. And so that's your abstract syntax tree representation. And that's what Bison builds. So if you're building an abstract syntax tree, it really only needs to be simplified, and you don't have to have a lot of stuff with it. Note that these would be tagged with the fact that they are indeed a number, so that you can figure out that they're type number later on. So Boknus-Nauer form. There's a bunch of different types of parsers. The LLK lookahead, LALR, K lookahead, and GLR parsers are all different types. LL is less powerful than LALR, which is less powerful than GLR. But LL is faster than LALR, which is faster than GLR. They each are restricted grammars. So an LL grammar is an LALR grammar, but not vice versa. An LALR grammar is not necessarily an LL grammar. What this means is that certain languages like C or C++ can be represented as LALR, but not necessarily LLR or LL. A lot of you may have heard me rant about Rust sometimes, something like that. They're actually at LALR point right now, but they're working on getting to LL because they want to reduce their grammar and try and simplify it so that parsers can parse it more efficiently. So if you look at these Ks, you'll notice that these two types have a K following them and GLR doesn't. K indicates the number of tokens we have to look ahead. So right here, if this is actually like represented as a token, for instance, this is a plus token, this is a minus token, this is a times token, this is a slash token, we don't know if this expression is actually one of these types unless we can look at this token. And that's called look ahead. And so a big point is being able to ask your Lexer for a new look ahead token and then seeing what that token is. And depending on how complex your grammar is, because there are some languages out there which actually need more than one token look ahead, 2 token look ahead, 3 token look ahead, that K is different. Bison and Yak only support 1 token look ahead. But Bison also supports a type of parser called a GLR parser, or a generalized left to right parser. And that means that, this is the look ahead left parser, sorry I didn't explain that. But that means that when we reach some sort of token that we can't identify, some expression we can't parse really easily, we're actually just going to branch. We're going to split off into multiple threads and just see what the hell happens. So we keep going, and we keep parsing those two as though they're separate different types of expressions. And eventually, supposedly, if our grammar is correct, one of those types just goes away, and we don't have to worry about it anymore. So we only continue on the correct path. It is very powerful, but it's also really slow, because if you have more, it's having to evaluate each expression time by time, and suddenly, if you keep having branches, you have this huge tree of possibilities that you might have to parse all of them for. Another type is a recursive descent parser. I was talking to Steve about this. GCC and Clang use recursive descent parsers because C++ and C are so complex languages nowadays due to their continual adding things to the spec and stuff like that, that it's very hard to parse them as an LL or an LALR. Using a recursive descent parser also allows you to have really good information about. So in case you're wondering why Clang is able to tell you, oh, this type's not supposed to be int start, it's supposed to be int, it's because they're using a recursive descent parser, and they can actually exit out of parsing when they find that error. And they can give you exactly where that error is and how long the line is that you need to edit it and stuff like that. And they can actually even suggest what's supposed to be right because they have this information from recursive descent. Backends. Backends are supposed to be replaceable. You have a backend that can do code generation, as I saw in my diagram before. Or you can have a backend that does interpretation, like the JVM. So in Java, for example, Java C is actually only the front-end portion of that compiler diagram. The IR is actually the bytecode representation. And so because of that, the JVM is essentially the full backend for Java and how it works. And so it takes the IR and it runs it on its system and an interpretation. Things like JIT, which is what the JVM uses, Rubinius, which runs on the LLVM, and PyPy, which is a JIT Python virtual machine, are a way of making a faster interpretation. So when you're interpreting code, say you're doing this by hand. You have this really big math problem, right? And you're going through and you have to do all the symbols by hand. But you start finding portions in that problem that repeat themselves. So suddenly you see, oh, I'm using this answer again here, and here, and here. Why don't I just do this once and save the answer for later? And that's what JIT does. So JIT sees that you're using the same subroutine over and over and over, and it goes, hey, I'm using that. Let's just save that for later. And it saves that portion of code, and it saves the result, and it inserts it back into where it's interpreting it. Which means that suddenly, when you're trying to interpret a statement, and you have the result, part of the result already, you don't have to do as much work to try and get to it. And that means that it's really fast. A bytecode VM, such as YARV or the Python virtual machine, are forms of interpreters, and they run on bytecode too. So why are you supposed to care about compilers and interpreters? New languages. For instance, Rust is a new language that is developed that is being targeted to replace, or not necessarily replace, but offer an alternative to C++ and operating system level languages. There are things out there like a language called Z, which is basically Lisp but with a different delimitation syntax. Or even strange languages that you haven't heard called ML, OCaml, F#, things like that. new languages are constantly being developed. There's a lot of languages out there. And not all of them are good, but some of them are interesting. And they offer new ideas into how to do things. For instance, Rust is really the first language that is offering type inference on a low level. You don't have to necessarily just declare that everything is type int or type float or type string or type char star. It simply knows that you're trying to do that based on the types that you're using in your program. Optimizations. A lot of the trees and tree optimization things that we learn about in class have actually been developed from when compilers were being designed and written for the first time. Because compilers needed to be so memory efficient and so fast, a lot of improvements were made into how, for instance, tree traversals are done, or how visitations are done on nodes. There are constant new discoveries in how syntax analysis and how people write code and the forms that people write in are done in the field of compilers and interpreters. There are really interesting developments. For instance, studies in language development. So I talked about Rust a little bit. GHC is a Haskell front end that has actually been ported to run on the LLVM backend. And so that's very interesting. And this is something curious. The LLVM IR is actually its own proper language, much like the way Java bytecode is its own language as well. So we're starting to see languages that are embedded inside languages or get turned into from languages that run on top of other things that run that language. So I thought this was apt. So dog, I heard you liked compilers, so I compiled a very simple compiler to let you compile an even more sophisticated compiler to ... I thought this was really good because I was listening to a radio talk about a week ago from one of the people who actually designed and wrote Lisp, the first Lisp. And he talked about how they wrote the interpreter by hand, and they thought it was going to be this big chore to try and turn it into machine code and get it to run and stuff like that. But then a person who was sitting next to them was like, that looks pretty cool, I'll help you out. And he hand compiled the interpreter in 5 hours. So the next day, they were able to run Lisp code that they had planned and didn't think were going to be able to run for months later the next day. And then they were able to build better Lisp interpreters on top of that, bootstrapping themselves up. So yeah. Here's a little self-plug. I'm writing a language called Brick. It has OCaml/Rust/Ruby style syntax. It's at this place, bricklang, github.com. If you're interested, you should check it out. There's a spec, and I'm working on an implementation. If you're curious and want to help me out somehow because you're curious in this sort of thing, I know it'd be great if people could help me out. But don't worry about it. So yeah, this is compilers, interpreters, and what they are. Thank you very much. If you have any questions, shoot. Anybody have any questions? I was planning for question time.
Brought up recursive descent. How does it compare in power to GLR?
Recursive descent is the most powerful. Those were actually in terms of least to most powerful. Recursive descent allows you the most control over how you deal with your tokens. And so, like GLR, with recursive descent, you have no limits into how many tokens you can look ahead. And because of that, it is easily the most powerful. It is also a pain to write, because for every single expression and every single parse possibility, you have to write a statement that can deal with that. So whereas things like Bison and Yak can simply write the code for you to deal with this, you would have to deal with each of these manually. Now that's not a big deal when you're dealing with like plus minus divide. You simply have a switch statement inside of a case statement in C or something like that, right? But when you suddenly have like if statements, how do you deal with blocks and other blocks that get executed because of the statements of blocks and things like that? So parsers get fairly complicated, especially when they're recursive descent. They do offer, as I mentioned, better debugging and verbose information, which is why very complex languages like C and C++ favor them, because you can get more out of it. GCC uses a recursive descent parser since 3.0. Prior to 3.0, Bison was actually designed for GCC. And so before that, they actually used Bison in the GCC compiler. But they realized that the grammar was getting out of hand. So they wrote a recursive descent parser instead. It took quite a long time, but they eventually got it done.
So why do languages that are in intermediate representation not, or do they, require parsers and lexers?
Okay, so a lot of times, intermediate representation is something called a single state assignment, an SSA, which means that it uses registers like your actual computer uses registers. And because of that, they do have their own Lexer parser sort of thing in there, but they're very, very tiny because they don't have to deal with a lot of, oh, I have to do tables and trees and figure out how the syntax works, because you already know how it works. And so it simply deals with translating that intermediate representation, the single state assignment, to the representation of the computer. And simply, all it does is basically rename certain registers to match the computer's registers.
Okay.
So that's all it does. Yeah. Does that answer your question?
Yes.
Okay. Any other questions? Language design, I'll talk about linkers if you really want me to. Yeah.
Why is your language called Brick? Just curious.
So, originally when I was looking at it, I wanted it to be like Rust. I'm a big Ruby developer. I do a lot of Ruby. But Rust is very low level and doesn't have the syntax of a syntax like Ruby or Python very much anymore. I thought Brick would be nice because Rust sounds very ugly. No offense, Rust or Mozilla, but Rust sounds kind of like a dirty name, and like Brick is similarly kind of like nitty gritty. It's also, I found it funny because we're on RIT's campus and we're Brick City, so yeah. Yep. So that was also sort of a reason why I chose that name. Yeah. Any other questions?
Can you talk about how GCC uses Lisp as its IR? That doesn't seem like parsing it would be trivial, like it would be for JVM bytecode.
Okay. So last year, okay, yeah. So in Lisp, does everybody know a little bit about Lisp and how it works or anything like that? Okay. Can I open up a text editor?
Yeah.
Awesome. Okay, so I'll do a little bit of a demo. Sublime. So a Lisp, for people who don't know, is a language that is composed of these things called S expressions. This is not going to be an in-depth talk, but it's going to be simple. An S expression is either a list represented by a pair of parentheses, and it can have elements like 1, 2, 3, 4. The reason S expressions are really good for representing, for instance, intermediate structures is you can say, okay, this is a list, right? And it has 2 children. And that child is a list of 1, 2, 3, 4, and a list of 1, 2, 3, 4. That's a tree. So because that's a tree, GCC can simply take its AST, its abstract syntax tree, and dump it into a Lisp, into S expressions. And then the S expressions on the other side, the backend can say, oh, I'll just read this into memory. And whenever I encounter a new list, I'll treat it as a child of my current list. And so it builds up the nodes. And so that's why it's a good representation for trees. The LLVMIR is SSA because they wanted it to be able to be generated by other front ends and stuff like that. The LLVM includes a framework for being able to generate this, but sometimes people want to go their own route and just generate LLVMIR, so it's really simple to do that. GCC intermediary representation is annoying to create. I actually looked at using the GCC IR as my backend and stuff like that. It's really bad. Generating GCC IR is gross. Don't do it. That's why the LLVM exists now. So yeah. Any other questions? No? Okay then. I guess we're done.